Lecture 3 begins. The subject of Lecture 3 is momentum transfer between particles and fluid. The fluid exerts drag and lift on the particles. The particles exert the reaction force on the fluid. I will explain the formulation of these forces. In the last part of Lecture 3, I'll show the equation of fluid motion considering the influence of particles. The drag and lift are the most basic element in multiphase flow analysis. Long before the word of multiphase flow was born, many scientists have been engaged in research to know these forces theoretically and experimentally. Theoretical approach has been based on the continuity equation and Navier-Stokes equation. The full Navier-Stokes equation is nonlinear due to the inertial force, and so it's very difficult to obtain analytical solutions. If the Reynolds number is small enough, the nonlinear term can be ignored. This assumption is called Stokes approximation. Under the condition that the flow is steady and no external force acts, the Navier-Stokes equation becomes very simple. Using the Stokes approximation, the drag force Fd on a sphere in a uniform string can be obtained theoretically as shown in the yellow frame. Next, I'll explain the momentum response time using the Stokes drag. Let's consider a particle, small spherical particle, moving in a uniform flow with the velocity u. If the drag is only force on the particle, the equation of motion is given like this. Substituting the Stokes drag and particle mass, the equation of motion is expressed like this. The dimension of the denominator on the right-hand side is time. This time is defined as momentum response time or relaxation time. The response time represents the vulnerability or the traceability of a particle to fluid motion. If this time is short, the particle will follow the fluid velocity quickly, and if this time is large, they will follow the fluid gradually. Let's see an example of the response time. The response time of 100 micron water droplet in the standard air is 30 milliseconds. Integrating the above equation under the condition of zero initial particle velocity gives the figure on the right. When the time equals the response time, the particle velocity reaches 63% of the final velocity. There is a non-dimensional parameter showing the flowability. That parameter is Stokes number or inertial parameter. The Stokes number is defined by making the response time tau v dimensionless with characteristic time type tau f. The characteristic time of a flow is obtained by dividing the representative length by the representative velocity. For example, in a pipe flow, the diameter or radius of the pipe can be a representative length, and the average cross-sectional velocity or the maximum velocity of the pipe center can be a representative velocity. If the Stokes number is less than 1, the motion of the particle and the motion of the fluid are almost in equilibrium. If the Stokes number is much larger than 1, the particle motion is not much affected by the fluid motion. The figure below showed how particles follow fluid motion in a pipe with shrinking cross-section. When the Stokes number is small, the particle velocity follows the fluid velocity quickly. When the Stokes number is large, the particle velocity does not easily approach the fluid velocity. This slide introduces the theoretical solutions of lift. If a particle is in a flow with a velocity gradient, or if a sphere rotates in a uniform flow, a lateral force acts on the sphere in addition to the drag force. This force is caused by the asymmetry of the flow around the particle, and the force is called lift force. Even if the force is downward, it is called a lift. Here I will introduce an analytical solution based on the Navier-Stokes equation. The analytical solution can be obtained only when the Reynolds number is low, as in the case of drag force. Lift due to the velocity gradient is called Safman lift, after the researcher's name. The lift that acts on the rotating sphere is called the Magnus force, after the researcher's name too. In 1852, Magnus derived the force acting on a two-dimensional cylinder rotating in the non-viscous fluid. Now the word Magnus force is used not only for the cylinder, but also for other rotating objects. The lift formula obtained by Safman is shown in the yellow frame. Below that frame, the conditions for this formula to hold are shown. When the velocity gradient du dy is not zero, as shown in the figure, the fluid element is rotating. When the fluid element rotates, the particle also rotates following the rotation of the fluid. The angular velocity of the fluid element is equal to half of the vorticity. Vorticity is a technical term in fluid mechanics. If you are interested in the vorticity, refer to a textbook of fluid mechanics. The Safman lift is perpendicular to the flow and is oriented in the direction of increasing flow velocity. Right figures show the Magnus force acting on a rotating sphere in a uniform flow. In this figure, the lift is shown in vector notation. Usually in multiphase flows, the rotation is produced by the particle colliding diagonally against the wall. A theoretical solution of this lift is obtained by Rubinow and Keller, and it is shown in the yellow frame on the right. This equation also holds for when the Reynolds number is small enough. The direction of lift is determined by the after product of the relative velocity vector and the angular velocity vector. The formulas shown so far are based on Navier-Stokes equation. As I said many times, analytical solutions are limited to the case of small Reynolds numbers. So many empirical formulas, especially for the drug, have been proposed for many years. The empirical approach dates back to Isaac Newton's time. In most textbooks, the empirical fluid drag is expressed by the equation in the yellow frame. The drag force CFD is given by the drag coefficient CD, the dynamic pressure of fluid, and cross-sectional area of the object. Several empirical formulas have been proposed for CD. The case shown in the figure, the path is stationary. The direction of drag is the same as the direction of the fluid. That is, the treatment is one-dimensional. However, in multiphase fluid, these directions are not the same and must be treated three-dimensionally. In the multiphase fluids, the direction of particle velocity is different from the direction of fluid velocity. So all of the drag force, fluid velocity, and particle velocity must be given as vectors as shown in the second yellow frame. The same equation and illustration as in the last slide are shown here. Many empirical formulas are available for the drag coefficient. Next, I'd like to introduce some formulas. First, converting the Stokes drag to the drag coefficient CD, its CD is equal to 24 over Reynolds number. The Schiller and Naumann formula is the most popular formula for multiphase flow research. Kravachko modified the formula of the Schiller-Naumann. This now formula is convenient when a cheap calculator is used. The formula that can be applied up to a large Reynolds number is that of Morsi and Alexander. The coefficient CO, C0, C1, and C2 are given empirically. If Reynolds number is in the range of 1,000 to 200,000, CD can be regarded as a constant 0.45. Isaac Newton dropped a ball from the top of St. Paul Cathedral in London to measure free drag. His result corresponds to constant CD. So the above constant CD is called the Newton drag. But the value of the constant obtained by Newton is different from 0.45. This is a diagram showing the relationship between the drag coefficient and the Reynolds number. When the Reynolds number exceeds 200,000, the drag coefficient decreases sharply. The radial number corresponding to this sharp decrease is called a critical radial number. This phenomenon is related to the transition from laminar to turbulent flow in the boundary layer on the sphere surface. This phenomenon has little to do with multiphase flows, and so it will not be discussed anymore here. The figure showed the result not only for spheres but also for objects of various shapes. As explained in the next slide, there are various influencing factors for drag coefficient. Various factors affecting the drag coefficient have been investigated. This slide showed examples of such factors: object shape, turbulence and unsteadiness of free stream, non-uniformity of free stream, rarefaction effect, compressibility of fluid, interparticle spacing, particle surface slip in the stream like a liquid droplet in the gas or the gas bubble in the liquid, blowing at a particle surface, etc., etc. Some influencing factors are negligible depending on the condition. For example, the effect of flow unsteadiness is negligible in gas-solid multiphase flow. The effect of non-uniformity of free stream is negligible in most of multiphase flows because the particle size is small enough compared with the size of non-uniformity. The rarefaction effect should be considered when the particle size is comparable with mean free path of gas molecule, as in the case of nanoparticle. There are too many research reports from theoretical to experimental formulas. Here, I refrain from introducing such studies. My explanation so far is mainly about the drag. Regarding the lift, I only show the theoretical formulas of Safman and Rudnapf and Keller. This slide and the next slide will describe the empirical formulas for the lift. When a spherical particle with diameter d rotate at an angular velocity omega p under a uniform flow of velocity u, the lift is expressed by the equation in the first yellow frame. CL is the lift coefficient, and it is given by the empirical formula. The direction of the lift is normal to the direction of u. This kind of form is found in regular textbooks on fluid mechanics. The direction of the particle velocity in practical multiphase flow is usually different from the direction of the fluid velocity. The axis of angular velocity is usually not perpendicular to this slide. The velocity of a fluid approaching the particle is the difference between the fluid velocity vector and the particle fluid vector. The lift vector is oriented at right angle to both the relative velocity vector and the angular velocity vectors. As a result, the lift is expressed by the equation in the second yellow frame using the relative velocity vector and the angular velocity vector. The direction of the fluid lift is determined by the outer product of UR vector and omega p vector in the parentheses. If you are unfamiliar with vector operation, please refer to the beginning of lecture 2. I explain vector product in a polite manner. The lift coefficient is usually given as a function of the spin parameter omega. The spin parameter is defined by the ratio of the equatorial velocity to the relative velocity of fluid and particle. There are not so many experimental data on the lift coefficient compared with the drag coefficient. Experimental data on the relationship between the lift coefficient and the spin parameter omega is shown in the figure. This result is quite old. The Reynolds number in this experiment is considerably larger than the Reynolds number in the usual multiphase flow, so it remained questionable whether these experimental results are applicable to multiphase flow. An interesting experimental result is observed in this figure. When the spin parameter is close to 0, the lift will be negative. This seems to be related to the separation of boundary layer on the surface of the rotating sphere. But this interesting phenomenon has little to do with the multiphase flow, so no further explanation is given for it in this lecture. If the lift coefficient CL is derived from the theoretical solution of Lubnov and Keller, the lift coefficient CL equals 2 omega. It is shown by the dotted line in the figure. Ignoring a negative lift, I myself forcibly made an empirical formula shown by the solid line in the figure. When I made this empirical formula, there were very few experimental data that I could refer to, but I suppose there are more data at present date. French research have proposed the formula shown in the yellow frame. This slide shows the formulas given torque due to the fluid viscosity acting on the rotating sphere. This force attenuates the rotation speed. Next, let's move on to the equation of particle motion. The figure on the left shows the forces acting on a particle when the particle is in a dispersed state at low or medium concentration. The main force acting on the particle is drag. When the particle is in a field with a pressure gradient, the force due to pressure gradient works, as shown in the figure on the right. When the pressure gradient is constant, that is, the pressure changes linearly, the force is expressed as gradient multiplied by the particle volume. Thus, the pressure force per unit mass is gradient P divided by particle density. When the particle concentration increases, the force due to the pressure gradient become larger than the fluid drag. At higher concentrations, the contact force between parts will become dominant over the fluid force. This will be discussed in detail in lecture 7. Ignoring the contact force, the equations of translational motion and rotational motion are presented in the yellow frame. Particle motion can be tracked by step-by-step integration using the time step delta t. So far, I have explained how to deal with drag and lift force. If the particle concentration is low, the fluid motion is not affected by the particle and only the particle motion is affected by fluid. This kind of analysis is called one-way approach. In practice, in many industries, cases of such low particle concentration are not common. And the particle motion also affects the fluid motion. This interaction between the particle phase and fluid phase is called two-way coupling. This slide was used in the explanation of the fluid particle mutual interaction shown in lecture 1. I showed this slide again for your reference. First, let's consider the case where the particle concentration is not so high and the particles are flowing in a dispersed state. Generally, if the particle volume fraction is less than 0.2, the particle phase is considered to be in a dispersed state. This value of 0.2 was set experimentally or for convenience. Here I will expand the equation and expression based on Lagrangian or Euclidean model. In this model, individual particles are traced, and concerning the fluid motion, the phase average velocity in the cell delta x, delta y is used. The phase average fluid velocity is the fluid velocity averaged in volume occupied by fluid in the cell delta x, delta y. So the fluid velocity is fixed within the cell. The phase average fluid velocity vector is denoted by small u. Now, the number of particles in the cell is assumed n. Particles have different directions actually, but only when calculating the reaction force, all particles in the mesh are assumed to have the same velocity vector v. The drag force acting on a single particle with diameter d can be given by the first equation on the first line. The total of drag force on n particles is represented by Fdn. The Fdn is obtained by Fd multiplied by n as shown on the second line. So the definition of the particle volume fraction alpha p, n can be expressed by the equation in the red line frame as shown in third line. Substituting this n into Fdn and arranging it, you find that Fdn is expressed by the form shown on the fourth line. Please note that alpha f is used in place of alpha p. As a reaction of as a reaction of FDN minus FDN acts on the fluid in the cell. The reaction force per volume Fp is expressed by minus Fdn divided by the volume V. So small fp is expressed by the equation on the fifth line. Please note the minus sign disappeared because U minus V is replaced by V minus U. Finally, Fp is equal to beta times V minus U. Beta is defined by the equation on the sixth line. This beta symbol will often appear in the following lectures. Let's try to change the form of beta using the radial number defined by relative bulk velocity large U and particle size d. The relative bulk velocity is defined on the first line. The radial number is defined by the first equation on the second line. From this equation, the relative velocity UR is expressed as a function of radial number. Substituting UR on the second line into the definition of beta given on the third line, beta is finally expressed by the form in the blue line frame on the fourth line. The CD is the drag coefficient acting on a single sphere in a uniform flow. When the particle concentration is so low that the interparticle interaction is negligible, the force applied to the fluid unit volume can be given by using beta in the above equation. When and U gave beta for the intermediate concentration by the equation in the yellow frame. If CD on the fourth line is replaced with CD over alpha F to 1.65 power, the beta matches the Wang and U formula. When the particle concentration becomes very high and the particle cannot maintain dispersed state, the particles come into contact. The fluid pushes the particle and the fluid is greatly affected by the particle due to its reaction. To express this force, we do not use the formula of fluid drag. Instead, an empirical formula of pressure drop in particular packed bed is used. Let V be the volume of the mesh and large U in the figure is the flow velocity obtained by dividing the volumetric flow rate by the volume of the mesh. The large U is called the bulk velocity. Small u is the phase average fluid velocity. The phase average fluid velocity is obtained by dividing u by the fluid volume fraction alpha f. Large u and small u are equal where no particles are present. The Ergon formula is the most common as an empirical formula for pressure drop in the particle packed bed. When the particle moves at the particle phase average velocity u, the bulk velocity large U should be replaced with the phase average relative velocity UR multiplied by the flow fluid fraction to apply the Ergon equation. delta P by delta X can be expressed by the equation on the last line. Finally, I will show the equation of fluid motion in particle fluid multiphase flow. This equation derived in lecture 11. Here, the derivation process is omitted and only the result is shown. The fourth and the fifth term on right-hand side represent the effect of particle on fluid. The first term represents the momentum change of mass transport due to evaporation or condensation, and the fifth term represents the reaction force from particles. The first term can be ignored if there is no mass transfer. Concerning Beto in the reaction force term, the Ergon equation and the Wen and U equation are used properly with alpha F equal to 0.8 as a boundary. It was Professor Gidasco who proposed to use properly the formula of Ergon and formula of U and U. I should like to make one note here. Many researchers after Gidasco have followed his proposal. However, beta in the above two equations is not continuously connected at alpha F equal to 0.8. Fortunately, so far there have been no report of any inconvenient problem caused by this discontinuity. There are various terms and expressions on the first line, but some can be ignored depending on the condition. First, the gravitational term can be neglected in gas-solid flows. If the particle concentration becomes high to some extent, stress terms such as viscous stress and turbulent stress can be neglected compared with force term with beta. Momentum change due to evaporation and condensation does not occur in the case of most solid particles. Considering this situation, the top equation is simplified as shown last. This is the end of lecture 3. Thank you.